for coming. I know that it would be nicer probably to jump into that water, refresh a bit. But yeah, let me start by writing a couple of things down. So I'll fix y and x to be compact, oriented, smooth manifolds. And let's say that, let's denote by m partial yx the space of smooth embeddings or y into x, embeddings I'll denote like this, that are fixed on the boundary. So one example that we already seen is classical knot theory, which I'll quite unconventionally think of this version. So I fix this 3-ball, and all my knots live inside, and they actually have this boundary. Oh, wait, my convention is this is green. So now I have to draw the figure 8 knot. It's a test. Okay, I think I passed. So this is the a long version of the figure 8. So sometimes these are called long knots. This is what I mean by fixed on the boundary and actually near the boundary. So we want all our knots to be have the same exact endpoints. And then you can just put any knot inside. And this version of knot theory is actually equivalent to the classical one. But for me, it's going to be easier with this version. Okay, by a smooth embedding, I think, let me just remind you. So this is a homeomorphism onto the image such that at each point the derivative is injective. Okay, and let's say our goal is to study topological properties of this space. So this is a space. I didn't say what topology I put on this. There is a canonical usual choice of the C infinitivity topology, which is like the most natural if you want to study smooth embeddings. So topological properties of this space. And what by this I mean, well, we can study just the set of components. And in this case, this is what really we do in knot theory. We study such objects, so embeddings of an arc. So this is an embedding of D1 into D3, right, with a fixed boundary condition. And studying connected components of this space exactly means you study points in this space up to the paths in that space, which are exactly smooth isotopies, right? So really, pi0 of embeddings of D1 to D3 is really is in bijection with pi0 of embeddings of S1 in S3. And this is exactly knots up to isotopy. But now you could just say, well, I can study for any manifolds y and x, maybe connected components of this, or why not also higher homotopy groups, maybe the fundamental group or higher homotopy groups based at some fixed embedding, I don't know, C. Or maybe you study homology. And so I'll try to, in this, this lecture series will not at all be about this general setting. I'm just trying to point out that what I'm talking about will have several instances of this. And I think this is at least the point of view that I take, that you can study embedding spaces in general, and maybe these homotopy groups of embedding spaces are just like generalized knot theory. Okay, it's like a multi-parameter families of embeddings that are knotted in some way. Okay, and I'll try to explain. Okay, so as Andras was trying to, this is a young audience, and he was advertising some problems. I'll try to advertise this field or this approach as something that's not been studied a lot, but that means it's very promising and it's not so hard to actually achieve some new results. as, for example, I don't know, studying smooth structures on S4. But I think it's also has, I try to convince you tomorrow, so in my second lecture tomorrow, I'll try to convince you, I'll give you some recent, I would say, breakthrough results in four-manifold topology related to diffeomorphisms of four manifolds that are obtained with maybe more of this perspective. And then the remaining 3 lectures will be by Jianfeng. He will talk more about like how one actually goes and computes this Kontsevich invariance. But I'm trying to give some more of a overview. Okay, so that's the goal. And what is this about? Well, it's about this idea. Let me first introduce notation. So for a fixed integer at least 1, the configuration space, unlike in András's talk, configuration space of a manifold X is just defined as the space of tuples of n points in X that are all distinct. So when I is equal, different than J, then Xi should be different than Xj. And you can think of this as really a subspace of this product, n-fold product of X, when you get rid of all the diagonals. So all the subspaces where Xi is equal to Xj for some I and j. So it's really a like actual natural submanifold of the product, although it's not compact. This is called the nth configuration space of X. Okay, and so let me now put the main idea here. Idea is to study these topological properties of this embedding space by scanning embeddings by points, by n points. And here you should really think n is sufficiently large. So we are trying to detect something about embeddings just by looking at by just putting some points on our embedding and letting them move. And you can imagine, like, even if I just have 1 point and it traces out a knot, like if I know where it is at all times, I know the knot, right? But now we're trying to simplify. We're trying to use somehow something about this topology of this configuration space to build some kind of invariance of embeddings, okay? And this will be, this will appear in several instances. So instance number 1, this is how it's originally appeared, is for studying classical knots. So for D1s in D3, this is something that belongs to the field called Vasiljev or finite type knot theory. And objects that appear in this setting are called claspers. Okay, I'll explain in a second what that is. Then number 2 can't really fit, maybe here, sorry about that. Just not to erase immediately. Number 2 is about diffeomorphisms of S4. And this is Watanabe's work in the last, let's say, 10 years. And he also has some kind of a version of claspers. Let me call them Watanabe's classes. In that setting, we have Watanabe's classes. And the third setting that I'll hopefully also mention tomorrow, is for the embedding space of arcs in any four manifold. And this is something which I studied and used some classical work, well, some work, let's say, a tool called embedding calculus. Embedding calculus. And here we have something called graspers. Okay? But let me put all these instances, all these examples in one diagram. What are we trying to do? So here we will have some kind of embeddings. Maybe I should explain why this is diffeomorphisms and not embeddings. It's really like embeddings of S4 into S4, right? When you take the the same source and target. Or you can also think, embeddings of D4 relative to the boundary. Was there a question? Okay, so for that, whatever our choice of embeddings is, 1, 2, or 3, we will have a construction that's going to go for some version of graphs. And this here is a combinatorial thing. Okay, it's completely described by combinatorics. But we will have some kind of a realization map that from a graph outputs an embedding or a family of embeddings or something in the homotopy group of the embedding space. That will be a construction. And a priori, we don't know anything about that. But then we try to construct an invariant using this scanning construction using configurations, using configuration spaces. And then we'll land here into graphs again, but modulo some relation. Some relations that will make this map well-defined. But what is interesting then is that this composition will be the identity map or the projection map. Like it will send the graph to the class of the graph in that group there, okay? And then what this shows is that, for example, if for every graph here, or that's the same as graphs here, you constructed something, that means that, this is just a projection, so it's surjective. That means that this map is surjective. You see, so, and that means that if you can compute this, and again, this is something combinatorial, and it's big, that means that you constructed many non-trivial things here, okay? So just by somehow playing this game of like constructing and having an invariant that detects exactly that thing. Okay, so I'll erase now everything. Hopefully this will work. Yeah, these slides are just to maybe help you follow what I'm saying. So it's the same exact thing that I said. But because there's not much board space. Okay. So what I want to say first is this classical setting of knot theory. That's something from the 90s that I think it's the best to start with that. Okay. So in this first example of classical knot theory, the graphs will be just trees. And they will have a univalent and trivalent vertices. So for example, I'll draw it like this. And they will have labeled univalent vertices, so with or ordered univalent vertices. And so then that one that's ordered, that's labeled by 0, I'll call the root. And these here are the leaves. And then there are also some trivalent vertices, okay? And the degree of this graph gamma is just the number of leaves. Okay, so that's graphs. Then this is like abstract graphs. Then what is an embedded version? Embedded version of a graph will be, well, we will first fix a knot. And you can, I think of it as the unknot. That's the simplest, D1 and D3. This one. And then we embed this graph into D3 so that the image of U and the image of this graph intersect exactly in these univalent vertices. For example, I can draw this one. It has 3 leaves and one a vertex like this. It has 2 leaves and the root. So this one here will be the root, and the other 2 are the leaves. And so here you see that we have this order on the knot, and that has to match up such that this is the first condition. The second condition is that order on U is equal to order in gamma. Is it clear what I mean? So always the root is the leftmost, and then I have the leaves there. Okay. And then we have the construction. So this is this Rn map that I was talking about. Sorry? Leaves? Leaves are, sorry, yeah, the univalent vertices. But that are not the root. Yeah. Yeah, sorry. This one here. Yes. And now I have the realization map. So out of this data of the knot U and the embedded graph G, I want to construct a new knot. So for this, I first have to, yes, so given G on U, we associate to it a framed link. Framed link LG inside of this D3. Okay, so how do we do that? Well, there is a recipe that we follow. First of all, this blue is not very different. So first of all, for the vertices, let's say you have 3 vertices coming out of this one internal edge. We want to construct a link now. We will replace this by the Borromean rings. Let me see if I can draw it. Okay, so there is the Borromean ring, so it's a 3-component link. And then, so this is not going to be the end. This will continue somehow. Okay, so that's how you replace the internal vertex by this picture. Then how do you replace the part where leaves connect to the knot? Well, the knot stays there, but this univalent vertex becomes also this, okay? And now I have to tell you how you connect this. So basically what I did is I explained how half edges look like. So for example, you just imagine that you cut here. I explained how these half edges look like and how these half edges look like. And now how do I connect them? Like when each half edge connects to this one, well, you just do like a hop link. So whenever you have this is replaced by the hop link. Let me just see which one do I want to do. Yeah. There are some conventions that I'm trying to skip. So the knot that you had on this side and the knot that you had on this side, they will become linked as a hop link. Okay. And so I said this is also a framed link. So what I'm also going to use here is blackboard framing, right? So blackboard framing means I will, whatever I drew here, you can also draw a push-off in the plane, a parallel push-off, and that determines your framing for your link, okay?
So is the U part of the new ring?
Sorry? No. LG is a link in the complement of U. Yeah. Okay. Sorry? Well, this just means that whatever this continues, this guy will also continue.
On the bottom left? Yeah, I don't understand.
This? Sorry. Yes, so this I was explaining how these 2 half edges that we explained there now get connected. When you connect this vertex to this vertex, the corresponding components will get linked. You will see in an example very soon. So I forgot to say one more thing here is that about the framings, that because we want to produce a framed link, we also need to have the framed clasper here. So this is called the clasper. So I forgot to say that as well. This is called the clasper. That's what I'm drawing in blue, although it probably looks white. So here, this also has a blackboard framing. So all these edges, if I'm drawing like that, that means that I can thicken them to little bands. Okay? But what I can also do is have a twist in a band. And then, so for example, like this. This can be extend my band. And then that corresponds to doing here the other crossing. So, okay. So I don't think it's important. We can also discuss it in yeah. Yeah. So okay, yeah. So the whole point is that there is a recipe. There is a combinatorial part is a graph. This is the embedding part. And the way that we draw it is using some conventions. So when I draw things, I try to keep, so that I can do the recipe, computer could do a recipe. And it's not important really for my lecture to know everything, but you can ask me in the exercising, yeah. So this is, I explained this half of this page. Now there is a definition of surgery on U along G. So what we want to do with this link, yeah. So this has, note that this has 2 times number of edges components. Okay, and you're going to see an example in a second. And now what we can do is we can do surgery on this link. And this might be something, abstract if you haven't seen it, but I'll do examples and you'll see that it's very explicit. But let's say that we define surgery on U along this class per gamma is denote that we can denote UG that lives, well, it's going to live in D3 surgered along this link LG that we just constructed. But this will turn out to be diffeomorphic to D3. And so what we want is, again, a knot in D3. We don't want to go to another manifold. But it will turn out that this is a trivial surgery. So i.e., what I mean by this, well, maybe I'll just show it here. You see here that the line down there, D3 LG, well, that is just, you drill out neighborhoods of all these components of this link that has 2E components. You drill out each of them, and you glue them back in using these framings that we somehow managed to fix, okay? But what will turn out is that this link will actually be, it's made out of a bunch of unknots. And many of them have actually 0 framing. We'll make sure that these components have 0 framing. And so that means that when you do surgery, you're really getting back the same manifold. You're not changing the manifold. But what that means in practice is the following. So let me show you how it looks on an example. Okay, so let's do the simplest example. And so let me just say that there is a way of explaining this without any kind of abstract, maybe a concept as surgery. You can really, again, explain it by just moves on diagrams. But it's very important for this later constructions to understand that there is some surgery involved. So let's do the first example of just, here is my U. And I just have one chord, okay? This is also allowed, no trivial invertices, and this is degree 1. It has 1 leaf, right? This is 0, 1, right? And I'm using the blackboard framing here. So that means that I replace this. Now I'm not sure about the crossings. Well, let's say it's like this, right? And now I need to do the surgery on this link. So it's really just made out of 2 unknowns with 0 framing. And when I do the surgery, that's not changing anything. But to identify the result of this surgery with D3, I actually have to move out parts of the link that really go through these components. They link these components, right? So what you do in practice is you slide this green over here. You do the handle slide, really, to slide this component out of the way. So that means that once you get over here, you'll have something like this. Okay? And then the link you can just erase, right? So this is somehow something similar to when you do also Kirby calculus and other things. But yeah, we can discuss it in the discussion session. What is important to note is that what we did, and this is the not UG. This is now not UG that still lives in our D3. There's no any link, no surgery, nothing. So what we did in total is just we took this unknotted arc, we took our finger and did a crossing change here, okay? So you can just remember that the way that you do clasper surgery is you take your finger, maybe on this first vertex, you go and do the crossing change across here, okay? That's everything. And it turns out that this move is very trivial. So something I define here at the bottom is that I say that not is n equivalent to u if you can go from u to that not using a clasper of degree n, right? So this means that this knot, UG, is 1 equivalent to the unknot, right? Because I just did a degree 1 clasper surgery, right? But, well, you know, up to isotopy, this is still the unknot. But what if you did some weird framing here? Maybe here you said, I don't want to do this framing, I want to do end twist here, right? So that means that here you would do end twists, right? And then you get something that's in general not going to be isotopic to the unknot, but you see that it's 1 equivalent to the unknot. And what we actually observe here is that K is 1 equivalent to U if and only if there is a sequence of crossing changes. From U to K. But of course, in D3, everything is related by crossing changes, right? You can always get to the unknot. So that means that if you just took your embeddings modulo this 1 equivalence, you're killing everything. Everything is 1 equivalent to U. Okay? Let me now do the degree 2 and try to see whether that's non-trivial. Ah, yes, yes. Sorry. Yeah, that's what, because I forgot to say that in the definition. Yeah, it's n equivalent to U if there exists a sequence of these. This is the simplest move you can do, just one clasper. But you are allowed to do a sequence of it because we want this to be equivalence relation, right? So, yeah, sorry. Let me do degree 2. And this, I erased my Borromean rings, unfortunately. Okay, let's do it for over. So here we say we fix this clasper. And then we do the link. Well, the link now has this 3 pieces. First, for these vertices, I replace it by these components. Then this one I replace by Borromean rings, again. Like this, okay? And then these Borromean rings, they correspond to this vertex, right? Now each of these edges is telling me to do a Hopf link with this guy, right? So here, again, there is some convention. Probably I'm not always following the conventions, but the point is that you can always make them to know which crossing we are actually, am I doing a positive or a negative or, you know. But something like this. Now I have a 6-component link. I have 3 edges, so that's why I get a 6-component link. And now I have the same story. These here are 0-framed unknots. As soon as I have 1, that means I can cancel this component with this component. But before I can do that, I have to slide this away, right? So I can just start by sliding all the green stuff from here across all of the link. And you see that and then I can just erase the link. And what I get is, first I need to redraw it in a more convenient way for me. Well, okay, let's say I'll just do it like that. I slide all the green away. So you can do it. You see that it's actually very simple. There's nothing mysterious. What we're doing, in essence, is just taking 3 pieces of our knot and summing each of the pieces into one component of the Borromean rings. So we're just adding Borromean rings to our knot. Okay? This looks like I messed up some of the crossings. Okay? Another way you can draw this that I like is using this commutator picture. It's also important for later. So what we're actually doing is, so this Borromean ring, so Borromean rings in this classical picture like this is actually isotopic to this picture. You put away 2 components, so this is an exercise for you to see, and then you take the third component and really make the commutator of the first 2. Here I take this, and here I take this, okay? And then you'll see, and then it's also isotopic to this picture. So this is something that's an exercise for you to do these isotopies. And it goes around here. And this will become later for the other important for the other constructions. Okay. And then an exercise is to see that this is, if I did it right, this is actually the trefoil. I think it should be the right-handed trefoil. And you can see that if you put some of the twists, like a half twist in these edges, you can also get the figure 8 knot. Okay. Are there questions about how I did this? Yeah? I meant like when I do this, that means that I fix the blackboard framing. But if I want to use the other framing, I'm allowed to do the other framing. And then I can, yeah. So what I said is that, when we fix, I fix this graph abstractly, but then I have to embed it somehow. And that embedding involves choice how I embed these edges. So that means that, for example, I'm allowed to do something weird as put a knot inside of this edge. Because that's part of the embedding. I'm allowed to do that. I'm embedding the graph. I'm allowed to do that. And I'm also allowed to pick another framing on every edge. Yeah, so for example, if I did that, then I would have this, this band here would have to follow. Exactly, yeah. It's like tying up this band in this knot, yeah, yeah. Yeah, so you can get very complicated things, yeah, yeah. Okay, so let me, right. So these examples are again drawn here. Yeah, and so what I wrote here is that there on the right, one can really see easily that these crossing changes are going to, knots modulo crossing changes are just going to give me the unknot. But if I do now this move, what this shows is the unknot is 2 equivalent to the trefoil, if you believe that this is a trefoil. It's, without this, it looks very complicated. But that means that even the simplest knot is 2 equivalent to the unknot. And with a bit of work, you can actually show that all knots are going to be 2 equivalent to the unknot, right? So that means that also this 2 equivalence will kill all the knots. But then the next one is non-trivial. And the next one is, if you take this pi 0 of embeddings of D1 into D3 modulo the 3 equivalence, then you get actually Z generated by the trefoil or the figure 8 knot. Okay, so people studied this. And then there was, this relation of n equivalence. And that's something that's actually more, so I didn't talk at all about facetive invariance. That's what actually first happened. And this version is somehow sometimes maybe called additive version due to Habiro and Gusarov. This version with claspers. Clasper is really a name that comes from Habiro in the 2000. But already in 93, Kontsevich showed that there exists a universal facetive invariant, okay? And in my language with claspers, what does that mean? Well, that's this theorem. And it's exactly the shape that I told you, right? It starts with graphs. With this shape, in this example, this is just trees. From trees, we can produce knots. So if I take a tree of degree up to n, that means it has up to n leaves, right? Then I can pick any clasper that has n leaves, and I can construct a knot by doing this clasper surgery on U, and I get some knot, right? So this is the map here. I go from a tree gamma to UG, where G is some choice. And note that here you really have to make some choice, right? But we do make it. We don't say, we don't need to be careful about that. We just make some choice. For every tree, we get a clasper, get a knot. And then one can show, and this is due to Habiro, Gusarov, and also Kohn and Teichner, that if you take free abelian group generated by this set of trees, that you can show that this is a surjective homomorphism of abelian groups. Okay? So you should be surprised why this at all is a group, right? It turns out, connect sum of knots. It's in general just a monoid, but here, when you mod out by this higher order relation, n plus 1, so here I'm doing, claspers only up to degree n, but here I mod out all the higher degrees. Then this turns out to be surjective homomorphism of abelian groups. Okay. What Kontsevich did is define this invariant Z that goes from that group into, again, something given by graphs. So on the right, it's, as I mentioned at the beginning, you're going to put this group, but modulo some relations, okay? And then this is some relation that actually turns out to be very natural, okay? But because I don't want to talk about this anymore, I'll just finish by saying that this was very important because basically it completely describes this group rationally. So the unfortunate thing about this invariant is that it's defined only over Q. So you have to tensor Q over, with Q over on the right. So that means that if there is torsion in this group, and it's not known if there is torsion, then you kill it. I mean, it's a finitely generated abelian group, but we don't know if it's, what is it? We just know that rationally it's described completely combinatorially as these trees modulo this STU squared relation that's drawn there. I'm not going to explain it. But this was a very important result. And I'm trying to just put somehow Watanabe's work on diffeomorphism into this context just to show you that this existed before. And then somehow his work is generalization for diffeomorphisms of four manifolds. Okay, are there questions about that? Yeah.
So there you mentioned that if you do a survey along hope links, then you just
Yeah.
cancel each other.
Yeah.
Well, I can believe that if there were no other components, but your hope link, one of the components is linked to like a Roman ring, right?
Yeah.
Why can you
Yeah, well, I'm using so I'm thinking of that upper guy as in the Borromean rings as some complicated thing. But then this other component that links the knot, I think of it as the zero-framed unknot. It's the meridian, zero-framed meridian of the first guy. That's what cancels that guy. But what I have to do is like I get rid of everything that goes through it. I slide it further down, and I keep sliding until everything really falls away from the link. You can slide everything away. Yeah. 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 Mm-hmm. Yes. So there is this. I should be careful if it's a sub, but basically saying that k is n equivalent to the unknot implies that it's also n plus 1 equivalent to the unknot. So you get a filtration where it's kind of harder and harder to be n equivalent to the unknot. Yeah. No. But what you can do is like you can reduce trees that have more leaves. Basically, by looking at that link, you can say, I'm going to just kill some part of the link and keep the rest of the link. So this is what Habiro does in his paper.
So
Yeah. It's always what?
It's always a tree.
A tree, yeah. But I'm doing a sequence of them. Yeah, that's what I forgot to say. Yeah, I'm doing a sequence of them. Yeah? Yeah. Yeah, sorry, the other way around. Yeah. It's decreasing filtration, yes. That's, yeah.
Second thing, what are the, first of all, do we know what these A, 1, 2, 3, 3K loops are specifically?
We know them in small degrees. Yeah, it goes like, you know, in degree 1, there's just one tree. This is the one that's there. Then in degree 2, there's just that tree. In the next degree, there are 2 trees, and then it's just, we know, I think it behaves exponentially. We know some things about it. Yeah.
I don't get the relations. Like, I see a degree 4 vertex there. That's weird.
No, it's not degree. It's just like, it's 2 edges that are just projected. So you ignore that crossing. I mean, abstractly, you know, this is, yeah. Yeah.
It's some under over.
Yeah, under over, yeah. Yeah, but it doesn't matter if it's under or over, yeah. Okay, but let's keep more questions for later. I'll also be in the discussion session. I want to go now to this. So now I'll just, to save time, I'm not going to write most of this, but it's going to look very similar to what he had before. So now we're going to this setting number 2, which was diffeomorphisms of Watanabe. Yeah, by the way, I will share all of my notes, so don't worry. So here, instead of trees, so note, what is the difference now? We don't have, like, we're not there. We had D1 embedded in D3. Now we're embedding the whole D4 in D4, right? There is no, like, a reference knot anymore, so that we kind of don't know what to do with trees. And instead, we use these graphs. We just have trivalent vertices. There's no univalent vertices. So, for example, that graph there, the theta graph, this one, right? It has 2 trivalent vertices and 3 edges between them, okay? So this is a type of a graph that now that will matter for diffeomorphisms of 4 manifolds. Okay, so we use connected trivalent graphs, and we're going to be in even dimensions, so in dimension 4. But I wanted here to point out that Watanabe also does work in odd dimensions and in other dimensions than 4, in higher dimensions as well. And then that's the abstract graph. We define its degree as the 1/2 of the number of vertices. We had 2 vertices here, so this is degree 1, okay? So this is the simplest one we have. And then we embed this. Now we have a 4-manifold X, and we want to embed this graph. What kind of choice does that involve? Well, if you think about that, in dimension 4, now you can't, I mean, there's no meaning to this, right? If you embed your graph and put a knot in there, up to isotopy, you can undo the knot, right? Because you have just one arc in a 4-manifold, right? But what you can do is, like, these loops, of course, can go around some non-trivial group elements, so in the fundamental group. So there are, again, some choices how you want to embed your graph. And actually, for most of the rest of this lecture series, it will be about S4, so you don't have to worry about it. There's no even that choice. And then you also want to frame the edges. And then once you have that embedding, then you can do the construction. And now I have to explain, well, what the trivalent vertex mean, right? Now I don't have univalent vertices. And I have to explain what the edge means. And again, we want to imitate, I guess, you know, Watanabe was inspired by this construction in knot theory. So what is the generalization of this Borromean link now? So I'll let you think about that. What would be the Borromean link in S4? So, or what is a Hopf link? That's the easier question. The Hopf link would be you take a circle and you want to draw its meridian, right? If you have a circle in S4, its normal disk is three-dimensional, right? So if I drew somehow, you pick a point and you have a normal disk, well, it's three-dimensional, right? The normal bundle is three-dimensional. So that means you can take a boundary, a sphere sub-bundle of the normal bundle. The fiber there is a sphere, right? So this is the Hopf link in dimension 4, in S4. Okay? And this is what's going to correspond to an edge. Okay. And what about the Hopf link? Well, what we can also do is imitate this second description of the Borromean rings that I said here. Instead of these two components that are circles, I'm going to draw two spheres, S1 and S2. And then, well, now reversing this play here, what is the normal disk of a sphere? Well, it's two-dimensional, right? So it has a normal meridian, right? And this one as well. And actually, this, the complement is like, S1 wedge S1, well, in R4. So it's completely described by these two meridians. And now we can also draw the commutator of these two meridians. And I claim this is a commutator. Like if you started here, you would go A, and then B, and then A inverse, and then B inverse, and then come back, okay? So what we are generalizing is this fact that Borromean rings is really describing some kind of a commutator relation between these three components. And you can see that when you erase any one of them, you can undo it. Similarly, like if in the commutator you put if you have a commutator of A and B and you put A to be 1, right, that what you get is BB inverse, so it's trivial. And this is what somehow, in the background of this whole theory, this is the very important thing to remember. It's about these commutators. And this is the right commutator to take here. Okay. Except that it's going to be a bit more complicated in this dimension 4. It will turn out that we can't replace. So I would like to say that we replace every trivalent vertex by this. But that doesn't quite work out, right? And so there is a little subtle thing here that, let me do it on the example of the theta graph. So if I draw, here is my theta graph, nicely embedded in S4 with this kind of, blackboard framing, no knotting, nothing. And how do I want to replace it by a link? Well, for each edge, I want to do this. For one trivalent vertex, I will do this. This trivalent vertex will be this link. But the other one will be a bit different. How do I determine this? Well, first of all, I do this convention. Did I do it here? I didn't do it there. First, we will orient the edges. So this is an additional thing that we have to add to an embedded graph. We want to orient its edges. I think here I want to orient like this and like this. And there is a way, so we have to orient so that each trivalent vertex has both incoming, at least one incoming and at least one outgoing edge, okay? And then for each outgoing, this means that we will have a sphere component. So here will be like S2, and here is S1. And this one here will be this circle, C1. And on the other side, you see that it has to be the opposite. For this S2 here, this S2 will come here. Like I'm replacing this by a sphere. Let me try to do it. And then this is a sphere. And then on this side, I have to have a circle, right? And that's the same is going to happen here. I have the incoming edge, so it has to be a circle. And here is going to be a sphere. So like put this graph here. Here I also have, now I did the exercise. I wanted this to be exercise. Okay, so here is the circle. This is this commutator guy here. Okay? And at each of these edges, I have a Hopf link. But now I have to figure out what to do here. And funnily enough, we're going to use the same link as before. So we can draw, again, this one as a sphere, for example. And then this one as a commutator. So here I can draw, again, this one. Yeah, sorry if it's getting small now. Okay? So, but I have a problem that this guy wants to be a circle. So what I can do is I can foliate this sphere by one parameter family of circles. So this circle comes here, attaches to 2 points, and then does the following. So here's a circle coming like with this, finger here, attaches to this arc. This doesn't look smooth, but don't worry. Here's a piece of the circle. And now you start moving this piece that's on the sphere around like a lasso. So you swing it around the sphere until it comes back, on this other side with these 2 points fixed, okay? So instead of having a single circle here, we have a one parameter family of circles. So in total, what do we get? S1, S2, here is a circle 1. Here is, let me call this C1, C2, but this is going to depend on the parameter t, with t is in 0, 1. And then here I have C3, and then here is the S3. And this sphere, is not really there. You have just this family of circles. Okay? And why is this interesting, and why will this still be useful? It's because now, instead of doing, one surgery on one link, we actually have a family of links that depends on a parameter. Everything stays the same except this guy moves, right? But it's a family of links. And for each link in that family, you can do surgery, okay? I guess I should be finishing, right? Okay, so maybe then I'll just explain the end of this slide. This is what I wrote here. Surgery along this Watanabe's clasper, Watanabe's link, is going to be a map from a sphere of certain dimension. Because I did just the theta graph, right? In the theta graph, I had just one parameter because I had one trivial vertex that this happened. But in general, if you have a graph gamma of degree n, that means it has 2n trivial vertices. And then n of them will be type 1, which means just use the standard Borromean rings. And n of them will be this type 2, which means foliated Borromean rings. So one parameter family. Okay? So you'll have n of them, and this is exactly the degree of gamma. This is why you will have an n-dimensional sphere mapping into BDIF, and now I don't have to explain this. But let me just show you what I wanted to explain. Yeah, here's the picture of the graph. And then I'll start, tomorrow I'll start with explaining this better. The point is that now, again, from a graph, we have a construction, and I claim that what we're doing here with these surgeries now is related to diffeomorphisms of X. And more precisely, it's the end homotopy group of the BDIF of X. And then we will land again into graphs. And in this case, graphs will be, we'll have to mod out by different relations. Okay, and then now looking again at this diagram, what this shows is that, this map, basically this Zn, that's Watanabe's version of Kontsevich integral, that map now is surjective. So that means that you're constructing many classes in homotopy groups of BDIF. If BDIF confuses you, this is the same as a shift of the diffeomorphism group. So for example, basically this shows that there are many classes in homotopy groups of diffeomorphism group of S4 that are non-trivial. And before that, and that's something that I wanted to talk about tomorrow, before that, it was not even known whether whether diffeomorphisms of S4 is just homotopy equivalent, to O5 or SO5, if I take, or let's say O5. So it was open problem, and then basically this shows that there's plenty of classes there. It's highly non-trivial. Yeah, so that's what was known as Smale's conjecture. Okay, then I'll talk about this rest of this slide tomorrow. Yeah, thanks. Sorry for going over time. Yeah. 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 Yeah, we have a link of circles and spheres, yes. And we can then do surgery on them. Yeah, so I didn't talk about handles yet. But like for me, a surgery is really just remove a neighborhood of this sphere and glue that back in using your framing, right? But yeah, it does correspond to handles, and I'll talk about it tomorrow. Yeah. Mm-hmm.
So we know, so what about the homomorphism of three spheres? Is it like trivial?
No, actually. So yeah, that's another version that's also people studied as well. I think there's also a version of Kontsevich integral in that setting that's called the LMO invariant. That's for Lee, Murakami, Otsuki. So there was and mainly they studied homology tree spheres. So you can do also the surgery on links that correspond to closed graphs. Yeah, definitely. But what happens in dimension 3 is that you change your manifold. You start with S3, you do maybe something like this, some surgery like this, and you actually go to another 3 manifold. But okay, so that gives you certain equivalence relation on, like a sequence of equivalence relations on 3 manifolds that you can study. But what happens in when you go to dimension 4 is that we will come back at S4. We do surgery on this, and we come back to S4. But we come back in a non-trivial way, and that's why we produce diffeomorphisms. Yeah, thanks for the question, yeah. Mm-hmm.
Do we understand the topological meaning of the low-dimensional invariant we can get from this? For example, for knots, we have the second derivative of the Alexander.
Yes, yeah. I think the answer is yes, and maybe it will be visible what these invariants are computing when Jianfeng does some computations. There is some meaning to that. And I also think that in odd dimensions, the first invariant also has some very explicit description, similar to the Conway thing, yeah. But then it gets harder to see, yeah. I like to think of them as like they are exactly the thing that detects this type of construction and this kind of a iterated commutator construction that's happening, yeah. Okay, tomorrow I'll start over with just like talking about 4 manifolds and not about this, yeah. Go ahead. Mm-hmm. Yeah, so this is exactly the topic of the rest of the course. Is going to be about Z. Yeah. So what I'm going to do tomorrow is try to explain, well, I didn't explain at all what I mean here, what I mean the surgery on this. I'm going to start over with that. And then I'm going to go in a completely different direction and just to show you that, yeah, sorry for going too long, but my point is that, okay, maybe you don't care about families of diffeomorphisms. Maybe this is like a different esoteric field of topology, but maybe you care about 4 manifolds, exotic smooth structures, and maybe also diffeomorphisms of 4 manifolds, right? Maybe you care about the question what is the mapping class group of S4? So we don't know, but it has been announced recently that there is at least one non-trivial element in there. So that means, there is at least one diffeomorphism that's not isotopic to the identity of the standard S4. And so tomorrow I'm going to concentrate on that, more on that question. What can we get from, like, imitating Watanabe's construction? Can we get something about, like, can we get examples of non-trivial diffeomorphisms of 4 manifolds? Yeah. So it will go in a bit different direction, and then Jianfeng will continue with just talking about these invariants. Yeah, thank you.